So now we're going to talk about variation. I'm going to look at some descriptive statistics. So I'm going to focus on why descriptive statistics are important. We're going to look about describing variation, visualizing variation, and measuring variation. So this is the window into some nice, very powerful, but quite simple statistics. So the first thing to bear in mind is that everything varies. Whatever you're measuring, whether it's an input or an output, it will vary over time. And we call that natural variation. And descriptive statistics is all about trying to measure and visualize the amount of variation at a basic level. So we're all familiar, hopefully, with measuring the mean of a distribution of an outcome. Sometimes we call that an average. So we plot something over time, and we can work out what the average of that is, and that gives us the middle, roughly, of our variation. It tells us the average value over time. We can also look at the maximum and the minimum, and that gives us a flavour of the spread of the variation. So, where does it begin and where does it end? So you might measure in your OTIF and you might have 95% OTIF, but the maximum is 100 and the minimum is 50. So it tells you something. It doesn't tell you everything, but it tells you something about your variation. But the problem with that is it doesn't tell you that much. So the example we talked about OTIF, so we could have a big variation in OTIF from a maximum to a minimum, so from 50 to 100, but that could look very different. So it could be all around about, for example, this one here, all around about 95 in the bottom one, and then we have one occasion where it was 50 and one occasion where it was 100. It's a different situation than the one at the top, where our OTIF might be varying from way down in the 50s, 60s, 70s, 80s, 90s. It could be all over the place. So the range is not a good measure of the variation. So the first thing we want to do is visualize the variation. So we use a histogram for doing that because it's quite a powerful way of looking at the variation. You can see more than if you just look at the numbers on a chart. And the way we do that is you divide the variation into what we call bins. So they're the horizontal columns, and you count the number of times you get a point in that bin, and that gives you like a frequency, and then you count those up, and so you can see you go from left to right, you end up with a frequency chart, which is what a histogram is, about the number of times you get a point in that bin. Okay, and then you can then turn it on its side and you get what's called a distribution curve, which tells you whereabouts the variation is occurring in relation to the mean and to the other points in the distribution. So if it's normal, it looks a bit like a bell, so that's what we call a bell curve. And the beauty of that is that you can see how it varies, and you can also see if it's not normal, but you can start to look at disturbances in the bell curve. We'll look at that later. So the next thing we want to do is think about that distribution curve and what it tells you about the variation. So in the first example we had before, you can see it's quite a big fat bell curve, and in this other variation you can see it's quite a squeezed bell curve. So straight away the shape of the curve tells you something about the variation that you're seeing. So what you end up with is you put that into a bit of analysis, a bit of software. You can see that you get a histogram, and obviously the number of bins determines the kind of quality of the histogram, does what it tells you. And you look at that example there, you can see it's kind of normal-ish, but there's something else going on there. So straight away you can see there's some stragglers at the right hand side in terms of what we call the tail distribution, and also there's some abnormality away from the mean in that example. Once we get a bit more into it, we want to be able to measure that fatness and thinness of the bell curve, and we do that using what we call standard deviation. Now, standard deviation is sometimes referred to as sigma, or a little kind of Greeky sign for sigma. And although the formula is very, very complicated, it's something you want to do on your own, but you can do this calculation in Excel. The actual concept is really simple, and all it's doing is measuring the average distance of each point from the mean. So it tells you on average, whereabouts the majority of the distribution lies. In terms of it's kind of a measure of the thickness of the bell curve. The reason the formula is so complicated is just because you have to use negative numbers and you have to square them so you get the same either side of the average line. That's why it looks complicated, but in actual fact the concept's really simple. So we'll go back to our example. If you look at the differences, so our fat bell curve has a standard deviation of 3.3, and that's the average distance in that example of the points from the mean. And then the thin bell curve, the standard deviation is about half of that. So you can see, start to get in a more technical measure of the extent of the variation in our particular sample.